When you fall asleep at night, you may not notice the moment your brain shifts into its deepest and most restorative state. There are no vivid dreams pulling you into strange worlds. There are no rapid eye movements beneath your eyelids. Instead, something quieter begins to unfold, a slow, powerful rhythm moving across the surface of your brain. This is deep sleep, unlike REM sleep, which is often associated with imagination and emotional processing. Deep sleep is grounded, physical, and stabilizing. It is the phase in which your brain waves become large and slow, moving in steady patterns known as delta waves. If scientists observe the brain during this stage using an EEG, they see broad, synchronized waves rolling across neural networks. These slow oscillations signal that billions of neurons are firing together in a coordinated rhythm. During this time, your heart rate slows, your breathing becomes steady and deep, blood pressure drops, muscles relax fully. External awareness fades almost completely. If someone tries to wake you during this stage, you may feel confused, heavy, or disoriented. That groggy sensation has a name: sleep inertia. It happens because your brain is emerging from one of its lowest activity states. Deep sleep occurs most prominently in the first half of the night. Early sleep cycles contain more of it, while later cycles shift toward longer REM periods. This distribution is not random. The body prioritizes deep sleep first, because it is essential for physical restoration. One of the most important processes that occurs during deep sleep is the release of growth hormone. Growth hormone does not only affect children. In adults, it supports tissue repair, muscle recovery, bone maintenance, and cellular regeneration. After physical exertion, the body relies on deep sleep to repair microscopic damage in muscle fibers. Without sufficient slow-wave sleep, recovery is incomplete. But deep sleep is not only about the body, it is also crucial for memory. Throughout the day, your hippocampus temporarily stores new information, names, facts, images, conversations. They pass through this structure first. But temporary storage is not enough. For memories to become stable and long-lasting, they must be transferred to the cortex. Deep sleep supports this transfer. During slow-wave sleep, the hippocampus replays patterns of neural activity that occurred during waking learning. These reactivations are brief and subtle, but they strengthen connections between neurons. It is as if the brain rehearses what it learned earlier, reinforcing important information and allowing less relevant details to fade. This is why studying all night often backfires. Without deep sleep, the brain cannot properly stabilize what was learned. You may spend hours reviewing material, but without slow-wave sleep, much of it remains fragile and easily forgotten. Perhaps one of the most fascinating discoveries about deep sleep involves the brain's cleaning system. For many years, scientists wondered how the brain clears metabolic waste. Unlike other organs, the brain lacks a traditional lymphatic drainage system. Instead, it uses something called the glymphatic system. During deep sleep, the spaces between brain cells expand slightly. Cerebrospinal fluid flows more freely through these spaces, washing away metabolic byproducts that accumulate during waking hours. Among these byproducts are proteins, such as beta. Excess accumulation of beta-amyloid has been associated with neurodegenerative diseases. Deep sleep enhances the clearance of this waste. In simple terms, deep sleep helps clean the brain. When deep sleep is consistently reduced, this cleaning process becomes less efficient. While occasional short nights are unlikely to cause lasting damage, chronic disruption may affect long-term brain health. This reinforces the idea that sleep is not passive inactivity. It is active maintenance. As we age, the amount of deep sleep we experience naturally decreases. Children spend a larger percentage of the night in slow-wave sleep, supporting rapid growth and development. Teenagers still experience substantial deep sleep, though circadian timing shifts later. In adulthood, slow-wave sleep gradually declines. In older adults, it may become lighter and more fragmented. Lifestyle factors influence this as well. Stress elevates cortisol, which can interfere with slow-wave initiation. Alcohol may initially increase drowsiness, but disrupts deep sleep architecture later in the night. Irregular schedules fragment sleep cycles, reducing the continuity required for sustained slow-wave activity. Physical activity, however, can increase deep sleep pressure. Exercise builds adenosine, the molecule associated with sleep drive. This encourages stronger, slow-wave sleep, especially when exercise occurs earlier in the day. Exposure to natural daylight strengthens circadian rhythm, making deep sleep onset smoother at night. Temperature also matters. The body's core temperature naturally drops in the evening. A slightly cool sleeping environment supports this decline, promoting deeper sleep. Subtle environmental factors can significantly affect sleep depth. Deep sleep differs from REM sleep in another important way. REM is emotionally vivid and neurologically active. Deep sleep is synchronized and restorative. REM integrates emotion and creativity. Deep sleep stabilizes memory and repairs tissue. They serve different but complementary roles. If deep sleep is repeatedly disrupted, the effects become noticeable. You may sleep for 7 or 8 hours, but still wake feeling unrefreshed. Cognitive clarity declines, physical recovery slows, immune resilience weakens, mood becomes less stable. The body does attempt compensation. After a period of sleep deprivation, the brain often increases the proportion of deep sleep during recovery nights. This phenomenon, called slow-wave rebound, reflects the biological priority of this stage. The brain restores what it needs most urgently. Deep sleep also plays a role in metabolic regulation. Hormones involved in appetite balance are influenced by sleep quality. When deep sleep is reduced, hunger-regulating systems become less stable. This may contribute to changes in appetite and energy levels. The silence of deep sleep can be misleading. There are no dramatic dreams, no internal narratives. But beneath that quiet surface, synchronized neural oscillations are coordinating large-scale repair. Brain networks are recalibrating, synaptic connections are adjusting in strength. Unnecessary neural noise may be reduced, preserving efficiency. Some researchers describe deep sleep as a period of synaptic downs. During waking life, neurons constantly strengthen connections in response to experience. If this strengthening continued without regulation, networks would become overloaded. Slow-wave sleep may help rebalance these connections, preventing saturation and maintaining flexibility. In this way, deep sleep is not only restorative but also protective. Each night, your brain cycles between lighter stages, deep slow-wave phases, and REM periods. These cycles repeat 4 to 6 times. Early cycles contain more deep sleep. Later cycles contain more REM. Both are essential. Deep sleep anchors the beginning of the night. It stabilizes the system before the more vivid REM phases dominate toward morning. Without deep sleep, the architecture of the night becomes unstable. When you consider sleep from this perspective, it becomes clear that hours alone do not define quality. Two people may both spend 8 hours in bed. One cycles smoothly through deep and REM stages. The other experiences fragmentation. The difference in next-day clarity can be dramatic. Tonight, when you close your eyes and drift into that first descent, your brain will begin slowing its electrical rhythm. Large delta waves will roll across neural tissue. Hormones will shift. Waste will be cleared. Memories will stabilize. Deep sleep does not feel dramatic. You do not remember it. You do not witness it. But it is one of the most powerful maintenance processes your body performs, and it happens quietly, every night. Deep sleep also influences how flexible your brain remains over time. During waking hours, your brain is constantly strengthening connections between neurons. Every new experience slightly adjusts the structure of neural networks. This is essential for learning. But if connections only strengthened and never recalibrated, the brain would become inefficient and overloaded. Slow-wave sleep appears to help rebalance this system. Some researchers describe this as a form of neural renewal. During deep sleep, overall synaptic strength may decrease slightly, preserving the most important connections while weakening less relevant ones. This selective adjustment prevents saturation and maintains cognitive flexibility. In other words, deep sleep may help the brain stay adaptable. There is also a relationship between deep sleep and pain perception. Studies have shown that reduced slow-wave sleep increases sensitivity to pain the following day. This suggests that deep sleep contributes to how the nervous system regulates discomfort. The body does not simply repair tissue during this stage. It also recalibrates sensory thresholds. Athletic performance is another area influenced by deep sleep. Reaction time, coordination, and muscle accuracy all depend on adequate restoration. When slow-wave sleep is shortened for several consecutive nights, performance declines measurably. Even small reductions in deep sleep can influence motor precision and endurance. Stress management is closely tied to this stage as well. Although REM sleep processes emotional tone, deep sleep helps regulate baseline stress levels.